Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy here at Foothill College in Los Altos, and it's a great pleasure for me to welcome everyone here in the Smithwick Theater and everyone watching us on the web to this first lecture in the 19th annual Silicon Valley Astronomy Lecture Series. These free public lectures on astronomical developments and discoveries are jointly sponsored by the Foothill College Science and Math Division, as well as by the SETI Institute, the Search for Extraterrestrial Intelligence Institute, the Astronomical Society of the Pacific, and NASA's Ames Research Center, one of the premier NASA centers in the country. We're delighted tonight to be able to welcome the director of the University of California Observatories, Dr. Claire Max. Dr. Max is the Bachman Professor of Astronomy and Astrophysics at the University of California at Santa Cruz, and as I said, the director of the University of California Observatories, which includes the well-known Lick Observatory, our first mountaintop observatory in the country, and then the Keck Observatory in Hawaii. She is the founder and former director of the Center for Adaptive Optics, a science and technology center supported by the National Science Foundation. And in her talk, she's going to talk a great deal about the miracle of adaptive optics. She's a member of the National Academy of Sciences. She has won the Ernest Lawrence Award in Physics and the Joseph Weber Award in Astronomy, in addition to many honors, including, I just heard that she's going to be one of the new fellows of the California Academy of Sciences as of next week. It's very interesting in this day and age to call a woman a fellow, but we won't go into that right now. We congratulate her on that honor as well. In addition to all her scientific work, she is the faculty liaison for education and public outreach at the Lick Observatory, a program that includes workshops for local middle and high school science teachers. She's had a long interest in making science intelligible for the public at large. And as witness to that, we're delighted to welcome her to talk today about a sharper image, seeing colliding galaxies with adaptive optics. Please help me to welcome Dr. Claire Max.
It's a pleasure to be here. I'm delighted that such a large audience is interested in astronomy, and I hope to tell you about some of the work that we've been doing at Lick and Keck Observatories. So I'm going to be talking about really two things. One of them is this new technology called adaptive optics, and the other is how to study colliding galaxies and what happens to the black holes that are in the core of these two galaxies when the galaxies collide. So two different topics, but related in a way I'll tell you in a moment. And the one slide synopsis of the scientific part is that most galaxies actually contain giant black holes with masses of 1 million to 10 billion times the mass of our sun in their core. Black holes are galactic trash bins. They suck in gas, which gets very hot as it spirals down into the black hole. And we can try and learn something about the black hole by watching the emission of electromagnetic radiation, light, as the gas falls into the black hole and gets very hot. But if each of the two galaxies that are in a collision bring their own black hole to the party, then the question is, as these galaxies collide, their giant black holes may merge together and form even larger black holes. And we'd like to understand how that happens and how that influences the evolution of the galaxies themselves in the future after a merger happens. And I need to say that in the history of an average galaxy in the universe, it's had a major merger, a big merger or collision with another galaxy roughly once in the 13 billion years of the universe. So this is something that happens to most galaxies, and it's not just some little side bizarre phenomenon that astronomers love to study. I wanted to add that this all sounds like hyperbole, but everything I've said here is a scientific statement that actually seems to be true. And I hope to explain a little bit how we know that. So I'll first talk about adaptive optics and laser guide stars, as Andy said, and then I'll talk about how we're using them to study these colliding galaxies. And I'll give a summary, and then I have some extra secret slides that I'll show at the end if I have time. So if you see me dawdling, raise your hand and say, hurry up. Okay, so here's the intro. So here's a telescope, and it's trying to observe, let's say, just a star, a regular star. The light from the star has to go through turbulence in the Earth's atmosphere, and that, it turns out, is what limits the spatial resolution, the clarity of an image that a ground-based telescope can take. So we all know that turbulence is why stars twinkle. My husband sometimes teases me that my goal in life is to take the twinkling out of the stars. But more important for astronomy, turbulence actually spreads out the light from a star and makes it into a blob rather than an ideal point of light, which it should be because stars are so far away that we can't see that they're extended objects. They ought to look to us like points, and they don't. So this is actually fairly serious. The biggest telescopes we have today on Earth are 8 or 10 meters across, and they have no better spatial resolution than a little backyard telescope that you may have used in your uncle's backyard or your aunt's amateur astronomer night. You are not seeing any more clearly with these giant telescopes than you do with a good amateur telescope. And that's because turbulence messes everything up, and we're trying to fix that. So I should add what a large telescope can do is gather a lot more light because it's got a lot more area. So it's used to observe very faint things. So here are 3 images of a bright star. Here's a long exposure image if I take a picture for a minute. It's about 1 second of arc across, for those of you who think in arc seconds. But if you took a very short exposure that's so short that it freezes the turbulence in the atmosphere, it's a snapshot in the best sense of the word, you wouldn't see a nice round thing at all. You'd see what's called speckles, these little dots, and the next time the turbulence changes, you'd see a completely different set of little dots. And if you add up enough of these different sets of little dots, you get something that's more or less round and that's more or less 1 second of arc across. And so what we're trying to do with astronomy is to correct for these distortions, and you can think of it in one sense as taking each of these little speckles and piling them on top of each other to get something that's just about at the ideal limit of what a telescope could do, even if there were no atmosphere. So you can use adaptive optics to dramatically improve image quality for many different contexts. I'll show you one in the secret slides at the end of the talk, but it's used in industry and medicine and lots of other interesting places these days. So I'm going to go into a little more detail. This is very short time exposures of a star, greatly magnified and greatly slowed down. So this is what the atmosphere does to the image of a star. It looks terrible, right? And if you add this all up, it's going to be some great big spot that big. And you'll see also that the middle, the brightest point of light kind of wanders around within the frame. So you have to correct not only all these big cloud of speckles, but also you have to try and correct so that the center of the stellar spot stays fixed and doesn't go off and wander off in these different directions. So how do we do that? Here's more cartoons. Here's your favorite star, and you want to look at this galaxy in detail. Actually, I should say, this is your favorite galaxy, and it happens to have a star nearby. And you can use the light from the star to measure the turbulence. And that works if the star is close to the galaxy, because the light from the star goes through the same turbulence as the light from the galaxy. So if you can measure it and calculate the shape on a computer to change the shape of a special mirror called a deformable mirror that literally puts wiggles on the surface of a piece of glass and cancels out the wiggles that the turbulence was trying to impose on you. And then the light from both the star and the galaxy, since they go through the same turbulence, are corrected and sent to whatever you want to measure them with, a camera or a spectrograph. And this is, in fact, done over and over again, so you're always almost correcting the turbulence well. You fall behind a little bit because the turbulence is changing and you can't necessarily perfectly keep up, but it's basically done continuously. And this is what you get from the same. On the left is the same image that you saw before of the star, and this is an image with adaptive optics, much smaller, much steadier. And what this doesn't show is it's also much higher intensity in the middle. So why is that? You have light that's spread over this huge area, and you're gathering it together with your adaptive optics, so it's just on 2 or 3 little pixels. So the intensity of the light in those pixels is going to be much, much higher. And that's shown in this different portrayal. So here's the star we were looking at. Here's what it looks like if I plot intensity in the vertical direction and X and Y in this direction on the sky. Here are these little speckles without adaptive optics. And with adaptive optics, I gather all this area together and put it into this, actually 3 pixels here, more or less. And they become much brighter than the area than they would have been. And that has a lot of advantages. You can see more detail, of course. But also, imagine you were trying to observe a faint planet around a bright star. So here's a bright star, and somewhere in here there's a planet. And, well, is that the planet? Is that the planet? Is that the planet? These speckles get in the way of figuring out how to image this planet. But of course, if you gather all the light from the star in a nice, neat place, you could easily see a planet over here or over here or over here. Easy is kind of a relative term, but you have a chance of seeing a planet. And there have been, I think, as of yesterday, 26 planets around other stars that have been imaged by adaptive optics. Of course, there are thousands that have been seen in indirect measurement methods, such as with the Kepler satellite. So here's an example of what this does for planetary science. This is an image of the planet Neptune in infrared light. 10-meter telescope, great big telescope, largest optical telescope, imaging optical telescope we have. Doesn't look like much. Here's with the Hubble Space Telescope in the same infrared light. Much, much more detail. But Hubble is only a 2.4-meter telescope. And if you look at it with a 10-meter telescope that's corrected very well, it ought to see things 4 times better, the ratio of 10 to 2.4 roughly. And sure enough, there's lots more detail on these cloud patterns that are on the planet Neptune. And we've even used these clouds, followed them as Neptune rotates, to map out the whole rotation pattern of Neptune's atmosphere. Here's another solar system object, the planet Uranus, with the Hubble Space Telescope. And now I'm showing you 2 different wavelengths of light. This is Hubble with visible light, and this is Keck adaptive optics with infrared light. And of course, I cheated, right? You can't see infrared light with your eyes. So what Larry Sromatsky did when he made this image was to say, I'm going to color the short wavelength infrared light blue and the long wavelength infrared light red, just so I can get a good comparison between these 2 images, one in visible light and one in infrared light. And you can see we're doing quite well for ourselves. Ground-based adaptive optics, AO, on large telescopes in the near-infrared has about the same resolution, maybe even a little better, than Hubble does in the visible. And so there have been hundreds and hundreds of astronomical research papers published which use both information from Hubble and from adaptive optics on 8 or 10-meter telescopes to look at the same detail in 2 different wavelength bands, and you can learn a lot from doing that. Well, okay, so how does all this work? I told you that you change the shape of a mirror to cancel out the turbulence. So this is like a 0th order approximation. Here's your deformable mirror, here's the reflective surface. And let's imagine that the incoming light has a wavefront that should be flat. If it's going to be perfectly focusable to a point, it should be a flat wavefront coming in. And instead, it's met up with some atmospheric turbulence, which in this case, of course, I'm exaggerating in saying that it made a square notch, just so I can explain myself a little better. It's actually wiggly and not square. But what I've done here is I've made a notch in the deformable mirror that's half the depth of the notch in the wavefront of the incoming light. So what happens is when this whole wavefront bounces off the mirror, you're sending the part that's in front a longer distance to travel than the part that's in back. The part that's in back only has to travel in and out to here, whereas the part that's in front has to travel in and out to here. And I'm giving the lagging part of the wavefront a chance to catch up with the part of the wavefront that was in front and arrange itself into a flat wavefront again. Now, we all know that nature doesn't make square notches, but it's more or less the same principle. So this is a cartoon of a deformable mirror. Think of a thin piece of glass. Think of actuators that are glued to the back that get longer and shorter when you put a voltage on them, basically. And there's a reflective coating, and the part of the wavefront that gets in front here, coming in, is made to travel farther than the part that was lagging behind, and so when the light bounces off the mirror, it's more or less of a flat wavefront that can be focused very well. So this is a manufacturer's cartoon of what one of these deformable mirrors looks like. Here's the front piece of glass. It's actually got, in real life, has a reflective coating on it. These are these actuators which push and pull on the deformable mirror. They're glued to the back. Now, you all know from fooling around with glue at home that this is not necessarily a precision thing. And when you say in a precision field, you've glued 4,500 actuators to the back of a piece of glass, you should worry. Because it's hard to get all the actuators glue curing at the same time. If you did it sequentially, the glue on the first actuator would be long dry before you got the glue on the last actuator even inserted. You have to think very hard about how to do this. And then these actuators are based in a rigid base plate, so when they get longer and shorter, they don't expand in both directions. They're fixed here, so they push and pull on the glass in front. And for the 30-meter telescope, TMT for short, which we're hoping to build, there are actually almost 5,000 actuators in the deformable mirror. So this is really getting up there, much larger number than we've been dealing with so far. Well, this is what a deformable mirror actually looks like. Here's the front, so the light comes in and bounces off. You can see it's a mirror. It's reflecting the pieces of this optical bench that are over here. Now, here's the secret. If you're being given a tour of a place that has an adaptive optics system and you don't have a clue what you're looking at because it's a big mess, there are all sorts of optical components all around. What you look for is an optic which has jillions of wires coming out the back. Now, why is that? Each of these wires gives a command, a voltage, to one actuator which is going to push or pull on this little face sheet in front. And so even if you have a mirror with only 400 degrees of freedom, 400 actuators, you're going to see a cable coming out that has 400 strands in it, and you can say, oh, what a beautiful deformable mirror you have, even if you don't have a clue what you were looking at. I've done that. Don't tell anybody. Okay, so there's one hitch in this, which is that you need a bright star nearby. So if your favorite galaxy has a star close by that's fairly bright, the light from it and the galaxy go through the same turbulence, and you can do what we've just been describing. But guess what? When you look up at the sky at night, it's mostly black, right? Not too many stars, considering that if you want to look at a random place in the sky where there's a galaxy that was born billions of years ago, and that's very faint, so your eyes can't see it, it's not going to have a bright enough star nearby. In general, less than 5% of the objects in the sky, of the positions in the sky, have a bright enough star nearby. So the star and the galaxy typically will be too far apart. This measurement of the turbulence will be fine if you happen to be looking in this direction, but it will be useless if you want to look at your favorite galaxy because the turbulence is different. So the idea that saved the day here was that if there's no nearby star, you can make your own star using a laser. Now, how does that work? There are a couple ways to do it. This is the way that we've been doing it at Lick and Keck Observatory. So it turns out that at a height of about 90 kilometers in the atmosphere, there's a layer of atoms that comes from little micrometeorites burning up in the atmosphere. As they streak into the atmosphere very fast, they get hot from friction, and they ablate away, and they leave their atoms up there. And so there's a layer where there's increased density of sodium and calcium and iron, lots of other metallic-like elements. And sodium is particularly useful because it has a very strong resonant transition, a spectral transition, like those yellow street lights that used to be all over the place. Those deep yellow street lights that you couldn't tell what color your car was because everything was yellow. So they're being replaced by LEDs, but think about that yellow color of light, and if you shine that up on these sodium atoms, they re-emit into all directions, and the directions that happen to go back into your telescope you can use to measure the turbulence. And it is working quite well. I have some anecdotes because in the 90s, when this hadn't ever been really tried for astronomy, I was a physicist at Lawrence Livermore National Lab, and they have a lot of expertise in lasers. So they had lasers equipment, they had people who were expert in using them and building them, and they had what's called dye lasers from a program to separate isotopes of uranium to make fuel for nuclear power plants. And a dye laser has the advantage that you can make it shine at any wavelength. You just prickle it with the wavelength that you want to have it laze at, and what comes out the other end is that exact same wavelength, but much brighter. So there was a whole building kind of over here, relative to this office building at Lawrence Livermore National Lab, which had nothing but lasers in it. And that light was being sent into an underground pipe to another building over here, which was the lab building where they shined it on uranium gas and tried to make this isotope separation happen. So we sent our yellow light through this same underground pipe, but we put a mirror down here in a manhole and just sent it up into the sky instead. And it was quite a show. This is a kilowatt laser, and you could see it for 10 or 15 miles away. And we had a little telescope here with which we looked at the sodium guide star, which was way up there. And this is the pipe that sent it up into the sky. It couldn't even follow a star, it was just fixed. But we wanted to measure this laser guide star spot in the sodium layer and use it to actually measure the turbulence, even if we couldn't correct for the turbulence with the system we had. There were some amusing moments there. First of all, there was a freeway kind of over here. And so my management at the lab said I had to meet the press and announce and explain what we were doing and announce to the highway patrol and the local police that we were going to send this laser into the sky on a certain night so that if cars stopped in the middle of the freeway, the CHP could get out there and shoo them along. And so people didn't panic in the nearby towns and so forth. So it worked quite well. The police loved it. Eventually, they sent a highway patrol person with the CB radio to be with us so they would know when we were about to fire the laser. And they had these radio communications with the rest of the police departments in the valley, the Livermore Valley. So my story is about UFOs. There was a lady in Pleasanton, which is about 8 miles away from this. Every time she saw this laser go up, she would call 911. And she would say, there's a UFO hovering above Lawrence Livermore National Lab. and it's sending down this laser beam and sucking up nuclear secrets. And she did it every time we fired the laser, so we would hear these nice CHP officers next to us say, oh no, you know, here's that lady from Pleasanton again. But anyway, that's my UFO story. It's true. So we first built a laser guide star for Lick Observatory. Here's the old 3-meter telescope that has a new lease on life now because of this laser guide star, and is doing great stuff. And then we built one for the Keck Observatory in Hawaii, which is two 10-meter telescopes that the University of California and Caltech and NASA jointly run. And at the time, this was considered to be sort of an oddball thing to do and a little bit far out, but guess what? Now, of all the telescopes that are on the summit of Mauna Kea, they're all running these lasers. So I don't know if you can see, but here's a bunch of telescopes. Each one is firing its laser. And it's become in general use now for the largest telescopes in the world. So I find that very gratifying. And I'm now going to tell you a little bit about what we use this for to learn about the universe. And I'm going to focus on this one area that I've been doing work in, which is to study colliding galaxies. So let's start out by saying, what is a galaxy? Not everybody is familiar with the terminology. A galaxy is a large system of stars and gas, and it has usually several million to several trillion individual stars bound together by the joint galaxy of the stars and dark matter that's in a halo centered on the middle of the galaxy. So there are three main kinds of galaxies: spiral galaxies like the Milky Way or Andromeda, elliptical galaxies, and ratty little irregular galaxies, which are typically much lower mass and look like they've had a train wreck recently, and they're one of the very interesting areas of research. That's a whole story in itself, but I'm going to focus on what happens when two of these gas-rich spiral galaxies collide. And I think I mentioned that at least these two kinds of galaxies, virtually all of them of a decent size, have a big black hole in their core. It's not so clear if these little guys do. So I have to start out by telling you a little bit about what is a black hole. Everybody seems to know. Here's a National Post, energy spewing black hole puts on cosmic show for astronomers. That's not what a black hole looks like, but it makes a great sales pitch. It's a region of space so densely packed with matter that nothing, not even light, can get out. So these are the densest places in the universe. To give you a sense of scale, if you took all the matter in the Earth and squished it down to the size of a grape, this would become a black hole. These are really dense. And how big is a black hole in space? Here's your grape, the nominal 1-inch grape. If you took the sun or another star like it and squished it down to 3 miles in diameter, it would be a black hole. If you took 1,000 suns and squished it to 3,000 miles, the size smaller than the Earth, but not a whole lot smaller, that would be a black hole. And if you took 100 million suns and squished it to 1/8 the size of our solar system, that would be a black hole. So that's just for scale. And as I said, black holes are the densest things that we know in the universe. And here's a cartoon to try and explain that not even light can escape from a black hole, and that's where the name came from. So if you imagine that you're on a planet like Earth, you know that if you throw a ball up in the air, eventually it'll fall down again from gravity, from the Earth's gravity. The mass of the Earth pulls it back. If you imagine in each of these circles you're adding more and more mass, if you throw the ball up with the same amount of force, it'll fall down quicker. It'll turn around at a lower altitude and fall back to Earth. And if the gravitational pull is so big that not only your ball, but even light can't escape, then that is when a black hole has formed. So a black hole is so compact and dense that the escape velocity is bigger than the speed of light, and we know that things can't travel faster than the speed of light, so light is stuck in the region of the black hole. Well, we want to actually look at the regions around the black hole and get a feel for how they're going to evolve when these galaxies collide. So how do we actually see black holes today? Of course, no light comes from the black hole. This cartoon says it's black and it looks like a hole, so I'd say it's a black hole, but that doesn't get you very far. So we want to be able to actually say things about what's happening in the immediate vicinity of a black hole. So this is a cartoon showing the very inner regions of a galaxy. There's a supermassive black hole, maybe 100 million or 1 billion times the mass of the sun. It's too small to see even in a cartoon. But there are hot gases around it that are slowly spinning around and spiraling in and falling on this black hole. And as they fall in, they get hotter and hotter. They emit X-rays. Farther out, they emit visible light, infrared light. And since this is a spinning disk, if we're looking at this side of the disk, the light approaching us will be blue shifted. It'll become bluer than its emitted wavelength. And light on the other side, which is moving away from us, will be red shifted. And if you haven't thought about this too much, it's like the Doppler shift of the horn of a train. So if you're standing here and a train is going by, when the train is in the distance coming toward you, you'll hear the toot-toot of the horn happening at a higher pitch. And after it's going away, you'll see it happening at a lower pitch. That means that the wavelength of the sound is getting longer for the train going away from us and shorter for the train coming toward us. And it's the same thing with light. So to try and measure, for example, the mass of the black hole, we can measure how fast the material on this side is coming toward us and how fast the material on that side is going away from us. And if the black hole is more massive, of course, the disk will be spinning faster and faster. So another terminology point, a galaxy core like this with an accreting central black hole where matter is falling onto it is called an active galactic nucleus. So I may mention the word AGN, and just think of this picture when you hear me say AGN. Okay, so how does adaptive optics help to see black holes or to see the regions right around them? We want to see this region very close to the core of the galaxy. We want to measure how fast the gas and stars are rotating around the black hole to weigh it, to measure its mass. And since we need to see things very close to the black hole, we need very sharp images. So that's where adaptive optics comes in. You can see things that are quite close to a supermassive black hole. Now, I said I'm particularly interested in colliding galaxies. These are just to convince you that galaxy collisions do happen. These are some Hubble Space Telescope images of colliding galaxies, mergers between galaxies. It usually looks like a train wreck after a while, like a billion years or so. These train wrecks will settle down and they'll become boring elliptical galaxies, as I showed you many slides ago. But when they're in this phase, they really are producing fireworks and lots of loose gas that can spiral into the black hole and make it shine. So it's now known that the size of a black hole is correlated with the characteristics of the galaxy as well. I don't have time to go into detail on that. Here is a scenario that was put forth by Di Matteo and colleagues in a computer simulation. Here are simulated two galaxies that are going to collide. And they get closer and closer. They eventually do collide. A lot of this gas falls into the black hole. And the black hole starts emitting X-rays and gamma rays and ultraviolet light like crazy. And it's emitting so much light that it actually can drive out a lot of the gas that's originally in these galaxies. And so a couple of billion years later, you'll just have the stars lying around left over from this collision. Most of the gas will have been pushed out by the emitted radiation from the black hole. It's a hypothesis. It seems in some cases to really apply very well. But we don't know if it applies only to the brightest active galactic nuclei, which are called quasars. Does it apply to weaker ones? Can we see observational signatures? And what happens if the black hole isn't accreting a lot, but we know it's there? We can measure its effect on its surroundings. So those are the general questions which we're interested in answering. So for the work I'm describing here, we looked at a sample of nearby gas-rich galaxies that had recent mergers, so that the two nuclei, the nuclei of the two galaxies, are close together. Now, you have to think close on an astronomical scale. So close in this case is within 3,000 light years of each other. That's close. And these are galaxies that are forming stars like crazy because there's lots of gas around. So they're very strong emitters of infrared light. And so their names are ULIRGs, ultra-luminous infrared galaxies. So if I refer to ULIRGs, that's what I'm talking about. We're looking at them with the Keck telescopes, two Keck telescopes adaptive optics systems. So here's an example. This is a galaxy named NGC 6240. It's a merger of two gas-rich galaxies. This is what's left over of the merger. It's still in the train wreck stage. It's relatively nearby, 300 million light years, that's nearby. It emits lots of X-rays and near-infrared light. It's got a double nucleus. You can't quite see it here, but I'll show it to you in a minute. And it's got these big tidal tails, which I'll try and illustrate why they happen. It also, fortunately, has a bright star nearby. And so we can use either this star or a laser guide star to do adaptive optics correction and look in the middle. We're going to look in a minute at the double nucleus, but I want to show you a computer simulation done by Josh Barnes of how a galaxy might end up looking so disheveled, shall we say. So here's a simulation of two galaxies that are going to collide. They pass each other by, but all the gas is being ripped out as they do that, and they go into orbit around each other, and what's left is these big tidal tails, and that's what this galaxy that I've been looking at has. So we're going to zoom in now on the nucleus here. Here's Hubble's picture in visible light. Here's Hubble's picture in infrared light. So now you can see the two nuclei for sure. And here's Keck's picture in infrared light. Lots more detail. One thing you can see right away is all these little bright emitting regions. Each one of those is a newborn star cluster. It was only born 10 million years ago with lots of young stars. So these collisions also make young stars like crazy. The question to ask ourselves is, we've got these two nuclei. I told you there were two black holes here. You can see them in their X-ray emission. Where are they? Is that the black hole? 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 You know, if we want to learn what's happening around the black hole, we first have to figure out where it is. So we can look a little more closely. Here I've blown up the image of each nucleus. That didn't help, right? I mean, where's the black hole? So fortunately, in many cases, you can get information from other astronomical observations, other types of astronomical observations. And in this case, each of these two nuclei was emitting radio emission that's completely characteristic of what is seen from these disks around black holes. And so we can use the radio emission. Here's the north nucleus, here's the south nucleus. We know these are coming from regions right around the black hole. They have a very characteristic spectrum and superb spatial resolution. Fortunately, Gallimore and Beswick made this image in radio emission at a frequency of 5 gigahertz. And so what we can do is just plop down the contours from the radio emission on our two nuclei that we can see at Keck with adaptive optics. And this one falls right on one of those point sources in the north nucleus. This one is actually a little farther north than we would have thought. And it turns out there's lots of dense dust in this region, and it's hiding the black hole even in infrared light. But now that we know where the black holes are, we can start asking questions like, how fast is the gas spinning around the black hole, and using that information to measure the mass of the black hole. So how do we do that? We are using something called an imaging spectrograph. The name of the spectrograph is OSIRIS. So what is a spectrograph? A spectrograph measures a spectrum, which is the light intensity as a function of color or wavelength of light. And an imaging spectrograph is actually a series of images, you can get an image of a galaxy in blue light, and then in the same galaxy in green light, the same galaxy in yellow light, the same galaxy in red light. Or another way to say it is, you have an image of the galaxy, and at each pixel in the image, there's a whole spectrum of light that's coming from the galaxy at that exact place. Now, why do we want to follow the colors of the light? Because we want to measure the Doppler shifts of the spectral line. So remember, I had this picture of a disk, and I said that you can measure how fast this part of the disk is moving toward us by measuring how much bluer the light is on this side than it started out. And you can measure how fast material on this side is going away from us by measuring how much redder it is. And so that's exactly what we're going to do. And the shift in wavelength of light is directly related to the velocity at which the gas, in this case, is traveling. Here, c is the speed of light. The change in wavelength divided by the wavelength is the change in velocity divided by the speed of light. So it's very straightforward. And here's one way to portray the data. So this is X and Y on the sky. Here's the data, here's a model, and it's color-coded, so blue is material moving toward us, and red is material moving away from us. This is a model, this is the actual slightly messier data, but you can see there's the position of the black hole in this case, and by looking at the patterns of this motion of the gas around the black hole, we can measure its mass. And in this case, we use two different methods, and it's about 1 to 2 billion times the mass of the sun. So these are big, hefty, supermassive black holes. And now that we know their mass, we can try and make sense of many of the other observations that are telling us about the region right around the black hole. And I'll tell you about this, what that is in a minute. So just a quick summary of what we found. We can locate where the black holes are. We can measure their masses by mapping the velocities of the gas and stars that are zooming around them, spinning around them. These guys really are supermassive, 1 billion times the mass of the sun. That's getting up there. I think the record is about 10 billion times the mass of the sun. So we didn't, in this case, we didn't hit the record, but there are lots of heavier ones. And the next question we want to think about is, will these two black holes, each one brought in by one of these galaxies, ever merge together? And if so, as black holes merge, they emit huge amounts of gravitational radiation, gravitational waves. I'll try and touch on that very, very briefly, because those waves have now been seen. So one of the things that can influence whether these black holes, here's another computer simulation, here are distant galaxies, they're going around each other, and in this case, there's lots of gas lying around, and they eventually do spiral in and merge. But if there were no gas in the nucleus, there's this famous thing called the last parsec problem. A parsec is 3 light years. It's an astronomical measure of distance. So if there's no gas in this central region here, you can end up in a situation where the two black holes are just spinning around and around each other forever. And since there's nothing to slow them down and have them lose angular momentum and get closer and closer together, they're just stuck. So this is called the last parsec problem. They would just spin around forever. And it's been shown in simulations like this that if there are giant gaseous disks around the black holes in the middle. The black holes can slow down by technically it's not quite friction, but friction with the gas. They move slower, they lose angular momentum, and they actually can merge. So we started out to say, okay, well, we can see this region very well. We have high spatial resolution with adaptive optics. Let's see what happens. Are these disks there? And it turns out they are. For 17 galaxies that we looked at as of a year ago, there are big nuclear disks in all of them. They're radii up to about 2,000 light years. They're moving at hundreds of kilometers a second in rotational velocity. In most cases, there's so much gas that they're vigorously forming stars, and that has interesting implications. So two binary black holes can lose angular momentum in several ways. One of them is they can scatter off stars in the nuclear region and just slow down, because each time they scatter off a star, they go a little slower. But they may have kicked out all the stars around them, in which case they get stuck in this last parsec problem. And we want to ask, not only can they be slowed down by gas, but what about stars? Can we somehow re-inject stars into the nucleus? So if we have a reservoir of gas from these big central disks, the gas can get in and slow them down, slow the black hole down. But they can also start kicking stars randomly into the nuclear region, so the black holes can slow down by scattering off the stars as well as scattering off the gas. So we think we've come a pretty good way to showing how these supermassive black holes can eventually merge, and this last parsec problem is a great theoretician's problem, but in real life, life is messy, as you saw in these pictures, and we think it's not that big of a deal. So why do galaxy collisions matter? Well, it turns out we're going to have our own galaxy collision. We have the Andromeda Galaxy. Right now is pretty far away, but people who study the relative motion of our Milky Way galaxy and the Andromeda Galaxy predict that in a few billion years, our galaxy will be colliding with the Andromeda Galaxy. So this isn't something that you should stay awake at night worrying about, but it kind of wakes you up to think that we may actually crash into each other here. Okay, so I want to now go on to the secret extra slides, which is to use adaptive optics to image the living human retina. So people studied how the eye works for many years by taking dead animals. I'm sorry about this, but that's what they did. They cut out their retina, and they studied the retina after it wasn't able to see anything, obviously. And how much better it is to actually study the retina as it's functioning and be able to use adaptive optics both to learn about how vision works and also for medical applications to look at what retinal disease does to the configuration that you can see in the retina. So the first thing you should be asking is, why do I even need adaptive optics to look at the retina? My doctor looks with that funny gadget in my eye, and presumably she's looking at the retina, and what's the big deal? Well, it turns out that, I'm sorry for the crudeness of my cartoons, but I've been told by my ophthalmology friends that this isn't too bad of a representation. You know, you have the white of your eye, and then you have in the middle, you have the pupil, which is where the light gets in. And at the edge, and there's a lens that focuses the light on the retina, and it's in the region around the pupil. And at the edge, it's attached to the rest of your eyeball. So, you know, in bright light, the pupil is much smaller than the size of the lens. When you go outside and you're all dazzled by bright light, your pupil gets small so that it won't let in so much light that you're unable to see anything. But at night, or when the doctor gives you that annoying eye drops, which they do in order to see your retina, the incoming light passes through these regions at the edge of where the pupil, where the lens and cornea are attached to the rest of the eyeball, and that's not perfectly engineered, so to speak. This is not a perfect attachment. There are optical distortions at the edges of where your pupil is attached to the rest of the eyeball. And literally, when the pupil gets big at night, or when you have those drops, you're uncovering the optically bad, imperfect attachment around the edges of the pupil, and you're looking through it. So the results are poorer night vision. How many of you at night, when you're driving, see flares around streetlights or halos around oncoming car headlights? It's very annoying. That's because you're looking through this imperfect attachment of your pupil to the rest of the eyeball. So it's annoying for us to drive, but it also means that the doctor or the researcher can't image the retina very clearly if they're looking in through that distorted region as well. And so that's where adaptive optics comes in. This is actually pretty bad. These are perfect eye, what a perfect eye would see as the pupil goes from being very small, only 1 millimeter across, to wide open, 7 millimeters across. So a perfect eye would see things more and more clearly, better and better spatial resolution as the pupil gets bigger. It's like with a bigger telescope, you're supposed to see more clearly. But that's not really what happens. Here's what happens. So as the pupil opens up, you're looking through more and more of this imperfect region in your eye, and the image of a point source gets worse and worse. And so what adaptive optics is doing is trying to take you from this sort of ratty image of a point source up to what it really should be if the optics in your eye were perfect. So this started out being kind of a clumsy way to do things. Here's adaptive optic systems. This adaptive optic system looked exactly like the ones we used for astronomy. This is like 20 years ago. Note the size of the computer. But the point is, you can put a human being here looking into an adaptive optic system and have a camera that takes a picture of the retina and get much better images of the retina than you could before. Nowadays, these things are like that big, but they're so crowded with optics that I couldn't show you what the details are. So I pulled out this old picture to be able to explain better. So here's a retinal image. This is without adaptive optics. This is with adaptive optics. You can see individual color photoreceptors called cones. These are what detects the colored light. This is the shadow of a blood vessel. The blood vessels are in front of your retina. You can even get the 3D structure of the retina at exquisite spatial resolution. The retina is pretty thick, and you can look at this is just looking at one layer, but you can look at every layer in the retina in great detail, including the nerves and the blood vessels and lots of other good stuff. You can also ask, what about color vision? Each of these cones is sensitive to a different range of color. We have red cones, green cones, and blue cones, meaning they're sensitive to red light or green light or blue light. And it turns out that perfectly ordinary people with perfectly normal color vision as measured by your eye doctor, or by those annoying charts that they show you. So these people have normal color vision, and look at this. This person, who I don't know if it's a guy or a woman, has far fewer red sensitive cones than this one, about the same number of blue sensitive cones, and way more green sensitive cones than this person. Yet they would both look at a white wall. White light is made of all colors, so you're looking at all colors of light on a smooth wall, and they would see a smooth wall. They don't see blotches, green blotches and red blotches. So this is fascinating. It means that your brain is doing lots of processing and smoothing and interpretation of what your complicated color detection system in your eye is sending to it. And there's lots to be learned here. I want to close with a movie. I said that you can image with adaptive optics blood vessels. So here's an image of capillary. And you can actually see the white blood cells zooming through this capillary. I love this. it's squirming. Now we know how to stabilize these images better. But when Austin Rorta first discovered these white blood cells, he had a grad student who he told to count the white blood cells as they went through, because he thought they could use it to characterize how healthy the capillary was. If the capillary was blocked, you wouldn't see so many going through in a given amount of time. So fortunately, they don't do it that way anymore, but this grad student got a great PhD thesis out of it. Anyway, that's the end of my talk. I want to thank you very much, and if you'd like to learn more about how you can support UC Observatories and adaptive optics, Natasha, sitting right here, is the person to contact. And thank you. This is a great audience. I'm going to make a sociological comment first, which probably will get me in trouble. Why is it that men always ask the questions and there are no women in line? Okay, and now I've put my foot in my mouth and I will extract it. And anyway, I encourage women to ask questions too. Go ahead.
I'm not answering that question.
No, don't answer that question. Bad.
I've been wanting to know the answer to this for a long time, which is, okay, so we're in Silicon Valley. We used to have these things called hard drives, and they would move, and they were very slow. And now we have silicon drives. They're a lot faster because there's no moving parts. The adaptive optics systems have lots of moving parts. Is there a non-moving part way to change the waveform?
Yeah.
Maybe with LCD or something.
Well, that's a great question. First of all, you can use LCDs as deformable mirrors. What the LCD does is changes the index of refraction in each pixel, so you can actually slow down or speed up the wavefront. The problem is that they tend to want light of a single color, and astronomers are greedy. They want to go all the way from the ultraviolet to infrared. And they're too slow right now. So they've been getting faster, but...
Slower than mechanical?
Yeah. Yeah. You have to, what's in these, each pixel is these long molecules, and they have to reorient. So it just takes some time.
Any other ways other than LCDs?
Yeah, well, yeah. So ideally, what you could do is have a perfect detector measuring the wavefront. Look at a star, and or maybe just look at your object that you're imaging, and if you can take an image faster than the turbulence is changing, you ought to be able to use software afterwards to reconstruct what all that turbulence did to your image. And that's called speckle imaging. And it works, but unfortunately, we don't yet have noiseless detectors. So you have to be reading out 1,000 times a second. Every time you read it out, it injects noise into the image. So you have to be looking at a really bright star or something, a bright source. So we did this many years ago for the planet Neptune before our adaptive optics system was working, and it worked well. But Neptune is very bright. And if you want to look at a faint galaxy at the other end of the universe, you can't do it that way.
Thank you.
Yeah, good question.
Yeah, my question is similar. What kind of response time adaptive optics system has? And I understand they're getting faster and faster. And also I would like to ask, what's the characteristic times of the atmospheric perturbation? I understand there are several modes, and what kind of modes, and maybe you may not correct for all of them.
Yeah, all good questions. So I'll give a practical answer. We have to run the Keck adaptive optics system doing the measurements 500 times a second, and we think that's a little too slow. We should probably be doing it 1,000 times a second. Of course, it changes from night to night because the speed at which the turbulence changes is partly determined by the wind that's blowing the turbulence across your telescope. So on a windy night, you'll have to go faster than on a still night. What was the second question? Modes. Oh yeah, good. So if you can decompose all the junk that the atmosphere puts onto your image of a star, say, into various kinds of perturbations of the wavefront, and there are big ones that just change gently over the mirror of the telescope, And there are very short wavelength ones which change many times across the mirror of your telescope, and the big ones tend to change more slowly than the little ones. So an adaptive optics system typically only tries to correct up to, they correct all the slow ones and some of the medium ones and none of the really jiggly little ones. And if you want to do adaptive optics at shorter and shorter wavelengths, right now we just do the infrared. If you want to go into the visible, you have to correct even more of these small scale modes, which means your adaptive optics system has to run even faster than 1,000 times a second. So the modes are related to how fast you're going to run your AO system.
Hi, thank you. Over the years of hearing discussions like this, they always talk about a lot of gas circling a star or what have you. I've never heard them actually talk about like what density, how many molecules per cubic meter, or how is it measured when it is considered a lot of gas in that environment?
Okay, it's all relative. So none of these densities are what we would call high, and the Earth's atmosphere is 10 to the 19th molecules per square centimeter. That is extraordinarily high for astronomy. And maybe in the innermost parts of one of these accretion disks you get up to that, but most of the accretion disk is much less dense than that. And in the matter between the stars, it's more like dense is like 100 molecules or atoms per cubic centimeter, and low density is like 0.1. So there's not much matter out there.
Yeah, no, I assumed something like that, but thank you.
Space is big and there's not that much out there.
Yes, how close does current AO get to the diffraction limit of, say, a 10-meter telescope at visible wavelengths?
So the diffraction limit is just what a perfect telescope would see if there were no turbulence. And right now at Keck in the infrared at a wavelength of 2 microns, we can get quite close to the diffraction limit. We've got a nice central peak, lots of good stuff. In the visible, not so much. So I think there are 2 Air Force telescopes that have very fancy adaptive optics systems that can do adaptive optics in the visible, but even they struggle a bit.
Okay, thank you.
What was the time frame out when you're doing experiments out at Lawrence Livermore?
Yeah, I want to say the early 90s. Is that the mid-90s? Something like that.
For galactic core collisions, and we've done the measurement of the neutron-star collision with the LIGO, and I'm wondering what the potential is of using LIGO to measure this class of objects.
Yeah, I was hoping you would ask. Gravitational waves, which are these distortions of space-time, the wavelength of the gravitational waves depends on the mass of the black holes that's going to merge. So the ones that the LIGO interferometers have measured, these are big installations in Louisiana and Washington and Italy and now India and Japan. They have measured mergers of black holes that are tens of solar masses, 30 times the mass of the sun. If you want to look at mergers of black holes that are thousands or 10,000 times the mass of the sun, intermediate mass black holes, you have to use this LISA, which is a space gravitational wave interferometer, same principle as the ones on the ground, but in space. And there's the different legs of the interferometer are separated not by a kilometer, but by 1,000,000 kilometers. And so they can look at much longer wavelength waves that are much lower frequency, that change more slowly. And if you want to look at these supermassive black holes, you can come back to Earth, and you can have an array of radio telescopes all around the Earth called a pulsar timing array. Each of these radio telescopes is timing the pulses from a pulsar, a neutron star, in the local neighborhood of the Earth extremely accurately. And a very long wavelength gravitational wave that's so long that it extends farther than the distance of two pulsars from each other, you'll see the timing of the pulsars changing relative to each other as the wave goes by. And unlike this space-based interferometer, which is going to go up in 2035 or something, this pulsar timing array is now called the International Pulsar Timing Array. It's got telescopes all around the Earth. And they're getting pretty close to being sensitive to billion solar mass black hole mergers. I wouldn't be too surprised if in the next couple of years they saw one. So when you get down below a billion, it gets harder, but we're getting close.
Thanks very much for an interesting talk, Dr. Max. I was wondering, are there relative advantages and disadvantages to having the surface that is active to having it be the primary versus a secondary mirror?
Yeah, good question. So in principle, you'd love to do this with the big primary mirror telescope, but they're heavy. So even the Keck telescope, which has hexagonal segments that are about that big across, their segments are about that thick. And so you're not going to be able to bend them in any realistic way. If you were to bend them, the force that you'd have to apply is so big that they'd probably break the glass. But what you can do is the light comes into a conventional telescope, it bounces off the primary mirror and goes up to a secondary mirror, and then comes down again to your instrument. And people are making adaptive secondary mirrors. And there are several big telescopes that have them, and a bunch of us are eager to put them on the Keck telescopes and on the 30-meter telescope. So I think that's going to be the next 10 years story, is these adaptive secondaries. And those are, right now, the biggest ones are 900 millimeters across, so a little bit less than a meter across.
Thank you.
Yeah, they're nice.
So I think you maybe partly answered my question, but I'm really curious how you make the adaptive mirrors. Like, how thin are they, and how do you ensure that when you bend them and move them, they stay smooth and not jagged so that you get a good image?
Yeah, so you have to people do these calculations before they go out and build one of how thick it should be as a function of how much you want it to move up and down in a local place. So if it's too thick, you'd have to push really hard on it in order to make it rise a certain amount, and that puts stresses on the glass, and also it means that if you push in one place, you'll be moving the mirror relatively far out. If you make it too thin and you push on it, you'll just get a very local region poking up, and then the rest of the mirror won't even know that the actuator has pushed. So that you have to balance the thickness with how far the what's called stroke is going to be, how far each actuator has to move, and how far apart they are. So there isn't any one answer for each deformable mirror that gets built. Somebody's out there doing the engineering of how do you balance those different things.
Okay.
Good
Thank
question.
you.
Yes?
What would happen if black holes collided? Would like one of them suck up one of them? Like, how would that work? Or would it just infinitely keep closing in, closing in, closing in, closing in?
Yeah, it's a good question. So if you have a small black hole and a big black hole merging, you could say that the big black hole sucks up the little one and gets a little more massive, and it's one big black hole. If it's two equal mass black holes, it's not so easy to describe in the terms that we would use from day to day, but they do merge together and form one that's twice as big. So yeah, they really merge. Unless they get stuck going around and around each other forever, but we think that doesn't happen.
Okay, we'll do two more.
Yeah.
Yes, I had a question about your I think it was your Neptune images you showed earlier. Can you pull those up? Is it possible to pull up? Might have been Jupiter, but I think it was Neptune.
Hold on, I have to find my glasses. Okay. Tell me when to stop. This is Uranus, that's Neptune.
Yeah, this one right here.
Okay,
What I was curious about is, I think, so that's the adaptive optics on the far right,
yeah,
and the center one was the Hubble image.
yeah.
But it looks like there's a contrast difference. So you can
Yes.
see the polar caps with Hubble, but you get, it seems like more contrast. You can't see the polar caps with the adaptive. I was wondering if there's a contrast issue with, or do you get better contrast or
Yeah.
different contrast?
Different. So the reason this is black, wrong one, sorry. The reason this is dark and this is dark is because methane in the atmosphere is, low in the atmosphere is absorbing the light of the sun. So this is all reflected sunlight. And if there are no high clouds, the sunlight goes deep into the atmosphere and gets absorbed by methane. And what these are high clouds, so the light gets reflected before it ever goes through all the methane and has a chance to get absorbed. So the contrast is higher here. It's like that picture I showed you of one star toward the beginning of the talk where you gathered all these little ratty-looking speckles together and got a really sharp peak, and that made higher contrast. So this light here is actually coming from these bright regions, and it's just not all getting collected in one narrow place because it's only a 2.4 meter telescope. But
So less spatial resolution.
less spatial resolution, right? Same thing here.
And are they capturing the same wavelengths? Or
Yeah.
one infrared and one visible?
Yes, this is exactly the same wavelengths.
Okay, thank you.
Yeah. Yes.
Does it take to form a black hole?
Okay, so there are many ways you can form a black hole. The most immediate one is you take a massive star and it reaches the end of its life and it blows up, and the central part of the star falls in and makes a black hole because it doesn't have any way to support itself. It doesn't have any pressure anymore. And so it just keeps falling in and in and in, and eventually the light can't get out. But there are also, we think, black holes that were started at the beginning of the universe and that grew bigger and bigger as billions of years went by. And probably lots of other ways to form big black holes as well. And one of the big questions is, if all the black holes early in the universe were relatively small, how did they get to be 10 billion solar masses? That's really big. So were there a lot of collisions? Did it suck in all these intermediate mass black holes? It's not well understood. It's a good question to ask. Okay, one more?
One more. Telescopes that are out in space, like Hubble, don't have this problem, as I understand it. Is that true?
So the James Webb Space Telescope, which is 6.5 meters across instead of 2.4 meters, Hubble, is made of segments. And so segments can be a little bit floppy, especially in space. The supports kind of float around a little bit. And so they have what they call active optics, which is they're always measuring where one segment is compared to its neighbor.
Mm-hmm.
And so they do the measurements. And Webb was designed a long time ago, so they measure it, they send the measurements down to Earth. There's a computer and a human on Earth who tries to figure out what the actual positions of the segment should be. And then days later, they send the signal back up to the telescopes about how to readjust the segment positions. So that is adaptive optics, but it's very slow. And you can imagine if they were making 20-meter telescopes in space, you'd have to really do that quite a bit, hopefully on board.
The question I'm trying to get at, I guess, to understand is, it seems like there's a trade-off between the cost of putting a telescope out in space versus the complexity of trying to do adaptive optics on Earth. Is there some point at which it's just better to go out in space and spend the money with rocket ships and do it that way?
There is, and that point evolves with time. So I guess the current thinking, it's not quite clear where the line is, where is that point? There's a new generation of 20 to 40 meter telescopes, which people want to build. They're called ELTs, extremely large telescopes. And today, there's a general consensus that you just could not do that in space.
Right.
You'd have to assemble things in space or make segmented mirrors that unfold many times as opposed to James Webb, which only unfolds once. And it's just beyond us. That's not to say it's always going to be beyond us. Maybe, you know, I wouldn't be too surprised if we're doing it in 30 or 40 years. But right now, the line is sort of shortward of 20 meters. And people are talking in NASA about launching 8-meter telescopes 10 or 12 years from now. And I think it's sort of up in the air whether they'll be adaptive or not, active or not.
Thank you.
Yeah, thank you very much.
Well, thank you. I wanted to say that for so many years, people on the ground have had an inferiority complex compared to space-based telescopes, and you've been a one-woman therapy session for all the ground-based astronomers. So thank you for all you do, and thank you all for coming.